All right, crystal field theory. First problem, number 7, looking at pictures of the d orbitals and which orbitals have the lowest energy in an octahedral complex. So octahedral, most common, definitely just memorize this pattern, and you should know that there's 3 orbitals on the bottom, lower energy, 2 orbitals on top, and the 3 in the lowest energy are going to be the x, y, x, z, and y, z, and the higher energy ones are going to be x squared minus y squared and z squared. Okay, so these ones here, lowest energy, okay, now why? So the key is with the octahedral complex, the ligands are on the x, y, and z axes. All right, so if you had a picture, with x, y, z, the ligands are, if the metal's in the middle here, the ligands are going to be located, we would say, directly on these axes. Therefore, the orbitals that are pointing at the ligands are high energy. So z squared, this one, and x squared minus y squared, because those essentially would be like this if you kind of saw them overlaid on here. They're pointing at the ligands, so they're going to be high energy. And the other 3 orbitals are situated in between the axes and therefore in between the ligands. So these point between the ligands. So if you're an electron in one of these, and keep in mind the ligands all have lone pairs that they're using to bond to the metal, so there's more electrons. So you're an electron, you don't want to be forced up against a ligand's electrons. There's going to be some repulsion there. So you want to have this kind of space in between the ligands to occupy, and that's just a lower energy state, right? It's not like the electrons actually have a desire. It's just what is lower energy, what is higher energy. And so this energy state is lower because it's in that way more stable. So you can think about more stable for electrons. Part B, we're taking this concept and applying it to a square planar geometry. On the handout at the end, I have some information, and I have crystal field diagrams for the main geometries, which are octahedral, tetrahedral, and then linear and square planar, which are less kind of frequent, but still somewhat common geometries. So you can look at them. If you want, you can memorize them, although I don't think it's necessary, but if you want to, you can kind of try and remember the pattern. But basically, the square planar geometry, in this geometry, you have the better axis here. So if this is like the x, y, and z, the ligands we're saying are just on the x and y axis and not on the z. So we take away those 2 ligands. So there's just, again, your metals in the middle. There's your square planar geometry. So the same concept, the orbitals that bump up against or push up against the ligands are going to be high energy. So the energy diagram for square planar geometry looks something like this, where you have several different levels, and it gets a little complicated towards the bottom, but the main idea, which you can figure out from the concepts, is that the highest energy orbital is always the one that's going to point mostly at the ligands. And so in this case, we get x squared minus y squared being the highest energy. So if I think about this one, let's maybe make it green. That's pointing directly at the ligands because the lobes of the orbital are on the x and y axis. So this is going to be highest energy because points directly at ligands. Okay, so the next one, next lowest, or next highest, I should say, is going to be the XY. That's the one we're looking for here. So second highest energy. And that one, essentially, if I kind of erase that, what I just drew. So this one is pointing right in between the x and y axes, but on the xy plane. So it's near the ligands, but not directly at them. So this one points near the ligands, right? And the other ones, which actually come out to look like this, again, if you look at the end of the handout, these are pretty complicated to actually see from the pictures because the z squared has a little donut kind of in the middle, which is in the xy plane, because otherwise that would be seeming to be not pointing the most away, but because of that little donut in the middle, you have some overlap. And then these, of course, have some x and z, or some, y and z. So there's some component that's in the xy plane and some in the z plane. So with these, I wouldn't worry about them. They're actually difficult to order, but hopefully the top ones make sense. Okay, unpaired electrons. We're going to fill in electrons into the crystal field splitting diagrams. First thing we want to start with is the metals oxidation state. So we have iron. Each of these cyanides are going to be -1, so that's -6. And we have iron has to add up to -3, so the iron is going to be +3 or 3+. Okay, so normally with iron, we have 4s2 3d6. We want to remove 3 electrons. We're always going to remove s's first, so we take those away, take away one of these, so it becomes 3d5. That's what's going to be important, is that d5 part. Those electrons get filled into the crystal field diagram. Okay, so we have a coordination number of 6, octahedral. So we're going to have 3 lower energy orbitals, 2 higher energy orbitals. That's just the octahedral pattern. These 5 electrons get filled in. In the next problem, we'll talk about high spin, low spin a little bit more. But for now, with the ligand being cyanide, if we look at the spectrochemical series, cyanide is strongest ligand. So that's going to mean that this splitting is large, or what that means is that we have what's called a low spin. So that these terms kind of go together: low spin, large delta. So when we plug in or fill in the 5 electrons, 1, 2, 3, instead of the 4th and 5th going up to the higher energy levels, they're going to pair down here. So what we're going to end up with is just this one unpaired electron. Okay, so that's important here. The low spin factor is important. It would change it if it was high spin. For the nickel complex, again, figure out the charge. Ethylene diamines, these are no charge. So nickel, because the whole thing is 2+, that means the nickel, therefore, is 2+. Start with the normal configuration. Always take away the s electrons first. So we just end up with d8. This is also octahedral. Remember, the ENs are bidentate. So we have really a coordination number of 6, again, because each of those bonds twice. So again, we have this pattern. And again, as I'll talk about in the next problem, D8 doesn't matter if it's high spin or low spin. You can try and fill them in either way. Fill them all in unpaired and then go to the bottom, or fill in the bottom, pair it, go to the top, unpaired, and then you'll still end up with 2 unpaired. So no difference between high spin, low spin if you have 8 electrons. So just note high spin, low spin doesn't matter. For D8. Okay. Now we have a vanadium complex. And again, chlorides are going to be -1. So we have -4 on the chlorides. Therefore, the vanadium will be 2+. This is normally 4s2, 3d3. So we can get rid of the s's. We're going to have 3 electrons. Tetrahedral, that's important to know because the diagram is the inverse of an octahedral. So if you can remember octahedral, tetrahedral is pretty simple. Flip it up upside down, and you get 2 on the bottom, 3 on top. And when you fill these in, again, we don't need to worry about high spin, low spin for tetrahedral because they're always going to be high spin. So tetrahedral is always high spin. Or again, what that means is small or low, small delta. So here we're always going to go unpaired in both levels before we go back down to the bottom, no matter what the ligand is. And so we end up with 3 unpaired electrons. Okay, so a few examples, and I think if you can do those, everything else is essentially the same thing. Okay, for this problem, we're looking at which metal ion in a high-spin octahedral complex has 2 more unpaired electrons than in a low-spin octahedral complex. Okay, so here's a little concept and a little rule that can help. So high spin, low spin only matters for octahedral if it's between 4 and 7 d electrons. So the high spin, low spin for D1, 2, or 3, or D8, 9, 10, they look the same. And if you can draw that out and do that to prove yourself. So kind of this here is our little quick rule. And also this you can represent or try to reproduce, that's the word I was looking for, on your own, just for practice and kind of make sure you understand how this all works. So I just took these D4, D5, D6, D7 and did a high spin diagram, a low spin diagram. Again, it's all octahedral. Remember, tetrahedral is always high spin, so we're not going to have this kind of issue with tetrahedral anyways. So you can look at then like the number of unpaired electrons, and you can write that down next to each one if you want. Like, oh, there's 4, here there's 2, here would be 5, here would be 1, here would be 4, here would be 0, here would be 3. Here would be 1. So then makes it easy to compare these and look at which one would be correct. You'd also would obviously need to figure out these metal ions, how many d electrons they have, and so that just again goes back to the rule of taking away the s electrons first. So hopefully you can do that. And just to show you what you should get, titanium 2 plus is D2, copper 2 plus is D9, manganese 2 plus is D5, cobalt 3 plus D6, cobalt 2 plus D7. Okay. So we know D1, 2, 3, or 8, 9, 10. Those would be the same either way. That would eliminate first two options. Here, so D4 would actually be correct if that was an option. You can see that there's two more unpaired with the high spin and the low spin. So that would be one that we'd be looking for. Or D7, right? That has two more unpaired in the high spin case. So cobalt 2 plus out of these choices is the correct one. Okay, hope that makes sense. Okay, number 10. Pretty interesting type of problem. And what kind of aspect of these that is really cool, I think, are that these coordination compounds have a lot of times these really vivid, intense colors, and indeed are what give a lot of gems and minerals their, beautiful red, green, blue colors. So with these problems, we can use crystal field theory and some basic concepts about light interacting with matter to predict the colors, at least respectively. Just if we know that, let's say these three compounds, one is yellow, one's blue, and one is red. If we know that, we can then, assign or match them to their color. Three things are needed, and that's going to be the spectrochemical series, which is again on the kind of information part of this handout at the end. There's just a general relationship between color and wavelength or energy of light, visible light at least. And then we have the color wheel. So with these three pieces of information, we can essentially work this out. So what you do is you are comparing three compounds. Usually these compounds are differing in the ligands, because if there were too many factors, we couldn't be able to tell. So what we have here is we have ammonia ligand or amine, we have the nitro or NO2 minus, and fluorine or fluoride. So if we look on our spectrochemical series, then we want to basically figure out where those ligands are respectively. And the way this spectrochemical series is laid out here is we have strong ligands going to weak ligand. So again, that would be kind of larger delta going to smaller delta. And what we did last time, or last problem, was again like this low spin again would be kind of this strong ligand case, and then high spin would be weaker ligand if that mattered, right? So between these three, we can see that the NO2 is the strongest ligand, and the fluoride is the weakest ligand, and then the NH3 is just kind of in the middle. So if we had the delta kind of in one column, we would have the largest delta being the nitro compound, the smallest delta being the fluoro compound, and again in the middle with the hexaamine cobalt 3 compound. So then the second piece of information is when it absorbs light. So we're going to look at two factors for the light. One is the absorption, one's what it appears. The absorption is going to be directly falling from the delta. So second thing would be Roy G. Biv is a way to organize the visible light from kind of weakest to strongest, or from longest wavelength to shortest. I think the energy case is better to think about in this case. And so then we have the color wheel, Roy G. Biv going around this color wheel showing the opposite or complementary color. So what we have is one compound appearing yellow. So if it appears yellow, it's actually going to absorb violet. If it appears blue, it's actually going to absorb orange. And if it appears red, it's actually going to absorb green. So what we really should be comparing to link them to the splittings and the ligands is what it's absorbing. So above these, I'm going to put absorbs violet, orange, or green. Okay, so let's take violet, orange, and green and look at the spectrum, the visible spectrum. Violet is the highest energy light. That's going to go with the strongest ligand or the largest energy change, because we know that electrons are going to have more energy when they absorb that light, so they'd be able to go to the higher energy level. And the smallest delta will absorb light of the lowest energy, which of these, violet, orange, and green, is going to be orange. So maybe I'll just write the whole word here. Therefore, green we would have in the middle between violet and orange. Right, so let me highlight these here. So then we can answer the question, if it's green absorbing, it appears red. And that's what we want. If it's violet absorbing, it appears yellow. If it's orange absorbing, it appears blue. So here is our answer for A, B, and C, red, yellow, blue. So not difficult in the concepts, but definitely a lot of backwards and inverse relationships, which writing things down and making columns, at least for me, has helped. Trying to do it in my head, I can tell you, it's easy to get mixed up. So I would just write some things down, kind of try to link them logically, and then find the thread that goes between the ligand strength and then what it appears. Okay, good kind of problem, and I hope that makes sense. Okay, for this problem, really concept problem, why is the hexa aqua zinc colorless where the hexa aqua nickel is green? Well, since it's the same ligand, that obviously can't be the difference. And the difference being the zinc 2+ ion has 10 d electrons. The nickel 2+ ion has 8. So remember from quantum mechanics and electron and light behavior that when a photon comes in order to be absorbed, it has to promote an electron, conservation of energy. So the electron has to jump up. Well, if you have 10 d electrons, then all your d orbitals are full. So therefore, if your light comes in, photon has the right energy, it won't be absorbed because there's nowhere to put the energy to electron. There's no possible electron transition. So basically, no light will be absorbed. So full d orbitals, so no possible electron transitions. So yeah, so the fact that zinc is D10, we have full orbitals not going to absorb at least visible light, so we wouldn't be able to, it would definitely be absorbing different kinds of light, which you can measure different ways, but wouldn't be able to tell just from our own eyes. Another one that's also clear or colorless is D0. So that's one that's good to note. Certain things like titanium 4+, manganese +7, stuff like that, you would have no electrons, so therefore you also would have no possible transitions. Okay, last problem here. We are doing a little bit of quantum mechanical calculations just with light and change in energy and determining the color absorbed from, or color absorbed, and then the color that it would appear from that. So what we ultimately we're kind of using this equation that is E equals hc over lambda, right? Or specifically delta E equals hc over lambda. And the thing that is important to remember is that when you're doing these are always calculated from energies of one photon or wavelengths of one photon. Mainly the energy of one photon, I guess. The wavelength would be the same. So the because if you use this 252 kilojoules, that's for 1 mole, you'll get a ridiculously small wavelength that won't make any sense in terms of trying to predict the color. So we want to find the energy of 1 photon absorbed. And so if to do that, we can take the units of 252 or kilojoules per mole, and we want it to be in joules, first of all, which is easy. And then because we have the per mole, remember we can cancel that out with Avogadro's number, right? So 6.02 times 10 to the 23rd. And that would tell us that 1 photon would have 4.19 times 10 to the negative 19 joules of energy. So then if we use either of these energy equations, the wavelength absorbed would be given by just solving for lambda, which is hc over E, or hc over delta E, whatever one you want to use, and then plugging in Planck's constant, speed of light, dividing it by this energy of 1 photon, and then we get the wavelength being 4.74 times 10 to the negative 7th meters. Okay. So if we convert that into nanometers, we just times 10 to the 9th. That's going to be 474 nanometers. Then you can go, you'll be given a little chart if you need to do this with the wavelengths of different visible light. You don't have to memorize that. And this, if you look up, this is blue light. So if it, remember, it absorbs blue, then it's going to appear, if we use the color wheel, the opposite. So this is going to appear orange. Okay, so good problem to be able to do. You can also practice going backwards. So if I told you this compound absorbed 474 nanometer light, you should be able to figure out the energy difference between the orbitals, which is the same as the crystal field splitting. So it's just the problem the other way. And again, just using that E equals hc over lambda formula. Okay, hope that makes sense, and let me know if you have any questions.